All right. So first, let's welcome Professor Wen and for his very expected talk, and we're very excited to have this colloquium for this year. And Jonathan is the chair of the colloquium, but he is on the plane, so I'm helping him to start the talk and the session. Albert is our longtime kind of admin and a member of this committee, and so Albert will help to moderate the talk and also the Q&A sections. And this is a very exciting kind of opportunity because we have been co-sponsored by all three major kind of parties and of the physics community by APS and the Chinese Physical Society and the Physical Society of Taiwan. And so it's a very rare opportunity that because for the COVID and many of other kind of obstacles and barriers, and a lot of communication has been either kind of reduced or interrupted. And now we see a very active and increasing kind of activities and very exciting opportunities for ahead to expect, and so to looking forward to. So I guess we're a little short on time, and so I let Albert to help to start the talk. And Albert, could you introduce the speaker, and we'll then get started. Thank you.
All right. Thank you. I want to start. First of all, I'm Albert Chang. I'm at Duke University, and welcome to the first of two exciting OCPA colloquia for this year. And let me mention that our goal with this colloquium series is to provide exciting, stimulating, and a highly interactive platform. So I'm expecting and encouraging many questions, and these will be there will be an extended period of time at the end for question and answer. So please take a look at the chat, and that gives you the direction to raise questions. So we have urged the speakers to not only tell us about established results, but also to include open questions and speculative ideas if possible. So in order to provide a really stimulating platform. Okay, with that, having said that, it gives me great pleasure to introduce Professor Xiaogang Wen, whom many of you are already friends with and aware of. Xiaogang has made many contributions to condensed matter theory and also to particle physics. He's well known for his theory of chiral liquids, one-dimensional interacting system at the edge of fraction quantum Hall effect, spin liquids, and he's probably the most important person who pioneered the concept of topological order, going beyond the traditional Landau paradigm for states of matter. Professor Wen has won many prizes, including the Buckley Prize of the APS and the Dirac Medal. And he's currently Cecil Ida Green Professor of Physics at MIT. So please give a warm welcome to Xiaogang.
Thank you very much. Thank you, Albert. Yeah, it's really a great pleasure for me to give this colloquium. And also, it's really a great pleasure for me to see so many friends. So we have been able to see in last few years, or maybe even more than that. So indeed, as Albert mentioned, that in recent years, the condensed matter physics, have a lot of activity and kind of very exciting time. And also in connection with the developed in particle physics, field theory, and some mathematical theory. And the reason is that we seem to enter into the new world of a highly entangled system. And that seems to connect a lot of deep physical phenomena. So today I try to introduce some of those connections. Hopefully, it's going to be stimulating. Yeah. And we know that our world is very rich, and we want to understand our words in a very unified way. But how really to get this understanding really through this cycle of discovery and unification? Because we first explore our world using a lot of experiments and observe a lot of phenomena and accumulate a lot of knowledge. But then we have too many knowledge, then we want to put them together and to have a kind of simple unified understanding. And then we keep discovering new things and we want to unify more and more things. So this cycle for discovery and unification is really represent our progress to get a deeper and deeper understanding of our world. Actually, each big unification almost like a revolution in physics. And each revolution really brings us into the new world, which in this new world, many fundamental concepts probably need to be changed. And the old language need to be also modified. And also we need to introduce new mathematics for this new world. Yeah. So the first discovery is this unification revolution is a mechanical revolution, which unified this fallen apple on the Earth and the planet motion in the sky. So the new world view is actually we view every object, all the matter in the world as a collection of particles, and these particles satisfy Newton's law. And then we get a kind of understanding of all the phenomena. And the mathematics behind this new theory is a calculus. It's interesting to note that this calculus is developed at the same time of this mechanical theory. So actually designed to formulate this mechanical theory. And the second revolution is like electrodynamic revolution. And it's unified the three very seemingly very different phenomena like electricity, magnetism, and lights. And this new world view is that I would say that discover a new form of matter we call the wave-like matter, and which can cause electromagnetic interaction. And this wave-like matter is very different from particle-like matter because it satisfies different law, which is governed by Maxwell equation. The new mathematics behind this kind of thing is a fiber bundle or gauge theory. And then we have this relativity revolution, which really unifies space, time, and gravity. Again, three very different things. But on the other hand, we can view this gravity as a discovery of a second kind of a wave-like matter, which is a deformation of space. And they satisfy Einstein equation, not a Maxwell equation. Okay. And this curved space, Riemann geometry became a new mathematical language for this kind of a second wave-like matter. Actually, the biggest revolution, I will say, is a quantum revolution, which actually unified this particle-like matter and the wave-like matter. They became the same. As a phenomena, they unified the phenomena of like hydrogen spectrum, the electron diffraction, and the black body radiation. So we got a very strange reality. The particle, the wave became the same thing, and the matter is neither particle nor wave, or both particle or wave. So it's really strange. So actually, the matter is a kind of particle wave-like matter. And here, the mathematical language for this quantum world also different, no longer calculus, but some algebra, linear algebra, and a tensor product. So if you really brainwashed by quantum mechanics, and you will see that actually the quantum mechanics really tells us is that the matter and the information became the same. They get unified. This is because the information, a change of information gave us a frequency. So in a sense, a frequency is a property of information representing the change. But according to quantum mechanics, the frequency is energy related by this Planck constant. And according to relativity, the energy is the mass. And both energy and the mass actually is a property of a matter. So you can see that in quantum mechanics tell us the property of information and the property of matter are deeply connected. So this really gave us a hint. Maybe we should not view information as something attributed carried by matter. Maybe information and the matter is really the same thing and should be unified. But how exactly the matter arises from information? The one idea is that to view the space as a qubits ocean, it's ocean for qubits. So qubits is quantum information, and the space actually formed by the collection of qubits. And then the elementary particle is a matter coming from a wave in this ocean. So this is possible because according to quantum mechanics, the particle and the wave are really related. The origin of a particle is the same as the origin of a wave. Okay, and also this entanglement between quantum qubits also gave us a sense of a space, because the only nearby qubits are entangled. So entanglement tells us what is neighborhood, and knowing the neighborhood gave us a sense of dimension. Okay, so this really in line of this some kind of Chinese philosophy. We can view the qubits as a 太极, and the two value of qubits as a 两仪. Then 四象 actually will be the 2 qubits. The 八卦will be this 3 qubits. But actually in our universe, we have much more than 3 qubits. We have a 10 to the 120 qubits at least to really form the whole universe, form the whole space. Okay. So this is the idea, very rough idea. Maybe this elementary particle and the space all coming from the qubits. But actually the story is much more complicated, because the elementary particle in our universe is quite complicated. In a sense, we can summarize this complicated property in terms of like 8 wonders of the universe, or 8 mystery. And certainly we have this identical particle. That's already very mysterious. All the electrons are absolutely identical. And also we have a wave which satisfies Maxwell equation, which is basically light. And we also have a wave satisfy Yang-Mills equation. That gives us a strong and a weak interaction. And we also have particles with the Fermi statistics. So where does the Fermi statistics come from? Again, it's a very strange thing. And also this particle with the Fermi statistics also carry a fractional angular momentum. And also this for weak interaction, only so-called right-hand fermion coupled to the weak interaction. We have also Lorentz invariance, and last we have a gravity, which is another kind of wave satisfying Einstein equation. So if you say the qubit is everything coming from qubit's motion or ocean, then the qubit ocean should explain all these, at least it's 8 features, 8 wonders in our universe. Can simple qubits produce this complicated structure? That is a challenge. So in condensed matter, this qubits motion is very much like a quantum magnet, because in quantum magnets we have electron spin up, spin down, and that's basically qubits. So therefore, in condensed matter system, one can use a quantum magnet to simulate the qubits ocean. So we're asking whether quantum magnets can produce a Maxwell equation which like simulate light, whether quantum magnets can produce some kind of defect in the spin configuration, which give us the Fermi statistics and the Dirac equation. Whether quantum magnets can actually produce a standard model, which describe electron, quark, and lepton, and many other things. Okay, so that's really the challenge. That looks like impossible because the quantum magnets is too simple to do that. So to see whether quantum magnets can produce a Maxwell equation, it really involves this principal emergence in condensed matter physics. So in the simple words, let's ask a question: why solid have a shape and the liquid do not have a shape? And this really because the solid and liquid have different wave equation. And this different wave equation coming from the different way a solid and a liquid organized. Say like in a solid, the particle organized in this very regular periodic array. And when you're deforming this this kind of organization, we can compress it, which get a density wave, which is longitudinal wave. We can also shear deform this array. This shear deformation will give us the transverse wave. And so therefore this regular array or crystal organization gave us this wave equation, which is supporting both longitudinal mode and the transverse mode. However, if we have a different organization, like we have random organization, then the only wave we can have is compressive wave, whether this density getting higher or lower. When you do the shear deformation of a random organization, the shear deformation is invisible. We do not do anything. So therefore, for this random organization, we have a different wave equation which contain only longitudinal wave. And because this wave equation do not have a shear mode, so therefore that's why liquid don't have a shape and the solid have a shape. So this is an example that the different order or different organization give us different wave equation. So therefore, we are asking what kind of organization gave us a Maxwell equation? What kind of organization gave us an Einstein equation or Dirac equation? And so if we find this kind of organization of some qubits, then we can produce this Dirac light. But however, for a long time, we thought this all the possible organization of the qubits are described by so-called symmetry breaking. Like in the crystal, we break translation symmetry, but in the random distribution, we do not break any translation symmetry. So that's a different symmetry gave us different organization. And so therefore, we study all kind of organization. That's basically the mainstream in condensed matter physics. Study different organization, different symmetry breaking, and a different wave equation from those organizations. And that gave rise to different property of materials. And from there, we really understand a lot of condensed matter system. But however, despite the success, however, we have a difficulty to find any organization which produce a Maxwell equation. Okay, so it's really very frustrating because after Maxwell proposed this equation, we really firmly believe it's a waving of something gave rise to Maxwell equation. But after 150 years, we couldn't find anything whose waving would give rise to Maxwell equation. So out of frustration, we declare the light or electromagnetic wave is fundamental. So we are not supposed to ask where they come from. So that's one way out. But certainly the puzzle is still there. If you don't believe this claim, you're still looking. But however, we got the breakthrough in 1980s in the discovery of this fractional quantum Hall states. Because the fractional quantum Hall states is formed by the two-dimensional electron gas, and we have a very precisely quantized Hall conductance describing different phases of matter for the two-dimensional electron gas. But however, all those 2D electron gas, all different phases, have same symmetry. We cannot use symmetry to distinguish them. So actually, this gave us a hint. This quantum Hall state contains a new kind of order, which we call topological order, which are beyond the symmetry. Before quantum Hall states, we really think that all the phase transition are really described by Landau symmetry breaking theory. So therefore, it's really like a beginning and end for condensed matter theory, because everything is symmetry breaking. We understand everything, then there's nothing to go forward. But actually, really, this discovery for fractional quantum Hall states really opened us to a new world. So we are not really at the beginning and end. Probably we are end of the beginning only. So this new world gave us new hope. Maybe this different phase of matter can give rise to Maxwell equation and the elementary particle. So what is this different world? What is this topological order? So let's do the analog. So we ask, what is a superconductor? So there's two ways to understand the superconductor. One is a microscopic characterization. So superconductor is a phase with a zero conductance and a quantized magnetic flux. And there's also microscopic mechanism. That is state where we have electron pair condensation. Similarly, for topological order, there's also a macroscopic condensation, or characterization, which is we can put this quantum Hall state or topological states on sphere, on torus, or on other this Riemann surface. And then we measure ground state degeneracy. So it turns out that for different topological space, we have a different degeneracy that reflect different topological order. And also another characterization is that this topological order can have a fractional charge and the fractional statistics using their excitation to characterize ground states. So that's a microscopic phenomenon. Microscopically, we find that this topological order actually is a state with a long-range entanglement. So it's a many-body state, but with a lot of entanglement. So that's gives us this new word, this long-range entanglement. So in the last 30 years, this field became more and more active. So in recent years, because this new graphene material, and we can have this new platform to really study a more exotic topological order. One of them actually is called non-abelian topological order, where we not only have a fractional statistics, we even have a non-abelian statistic. It's something really strange. And so therefore, in double layer graphene, we have these two papers, which kind of also observe this non-abelian statistics, non-abelian quantum Hall state in a quite a favorable situation, not too low temperature. And also more recently, we even observe this quantum Hall state without magnetic field. It's called the fractional quantum anomalous Hall effect. And again, there's two samples. One sample is a TMD sample. Another is a multi-layer graphene, ABC stacking graphene. And they see this. They even see the quantum Hall state and also fractional quantum Hall state without magnetic field. So this is a very exciting news, because it's really that this indicate that this moire material or this graphene material is a new platform which demonstrates a very rich, strongly correlated phenomena, and we're really hoping more to come. So actually, we may discover. I'm hoping to discover anion superconductivity in this kind of material. So let me try to explain what is a long-range entanglement. Because the topological order or this new phase matter of this non-abelian statistics, all these things are connected to the long-range entanglement. But what is entanglement? So certainly, let's get an example of unentangled state. We have two spin, one spin up, another spin down. That's an example of unentangled states. Then here we have an entangled state. We have a superposition of up and down plus down up, and that's a entangled. Then we may have a more entangled state. We have up, down, down, and up, down, and down, up. They all superposition, all four possible configuration. But here is some example. When you do too much, you get nothing. Because this superposition 4 state turns out to be unentangled. Because it's a product of a spin in x direction. It's a first spin in x direction, second spin also in x direction. So actually this is unentangled. So this gives you some taste that the entanglement is a little tricky. It's a superposition, but not a superposition of everything. And the typical system we have in condensed matter are usually unentangled, like antiferromagnets. It's up and down, up and down. So this kind of unentangled state, antiferromagnetic. But we may have a dimer state which are entangled, like in a pair of spin, they form an up and down, minus down, up, a spin singlet. So therefore, we got an entangled state. This is a dimer state is entangled. But this one is a short range entangled. Because if you think two lattice side, two spin as a one side, then there's a product state of a spin singlet. It's still product state is singlet. So again, it's unentangled. So therefore, the long-range entangled state is something beyond all this. But the usual state we are familiar with, like a crystal, antiferromagnet, ferromagnet, they're actually all kind of unentangled or weakly entangled. They are not long-range entangled. So therefore, the long-range entangled state is something not this, something beyond this. Okay. But how to get something beyond that? And one way to do that is we should make a superposition of different configurations. But we should not summing over all configurations. Okay. One way to do so is the following. We consider a spin system, and we view up spin as a background. And the down spin form a string. We assume down spin always form a string. And then we consider a superposition of all the strings. And so that's a partial sum of a spin configuration, not summing over all possible spin configurations, but only part of a spin configuration. And this sum of a partial spin configuration can be viewed as a string liquid, because the down spin from a string and the string from a superposition that gives us a string liquid. Actually, this string liquid can also be viewed as a string condensed state. It's a long-range entangled state. Actually, this long-range entangled string liquid is very magical. Actually, give us what we want. So, for example, this string liquid actually gives us a Maxwell equation. I already talked about the particle liquid. Have superfluid is a particle liquid. We have a particle in random distribution, and we have a density of a particle. But that one do not give us a Maxwell equation. But however, we have a string liquid, which do not have and, just closed loop. This string liquid can give rise to Maxwell equation. Why? Because we ask, what is the fluctuation for string liquid? What is the deformation for string liquid? Well, it's very simple, just a string density. Somewhere we have a more string, other place we have a less string. So this string liquid gave us a string density wave. But the string density wave is different from particle density wave. The string density wave is described by a vector field. Okay, so because the string have orientation, in some place we have a more string in certain direction. So this kind of thing are really described by vector field. Okay, but once we have this vector field describing a string density wave, then we should have an equation of a vector field which give us wave equation. But this vector field have no divergence. This is really because the string cannot end. If a string cannot end, then the density of a vector field can change. The density of the string can change only in the direction perpendicular string. Along the string, in order for a string to end, along the string, in order for string density to change, the string must end. If the string cannot end, the string density cannot change along the string, but only change perpendicular to the string. So therefore, we have a vector field with a zero divergence describing string density wave. Then you ask, what is the simplest wave equation which govern this divergence vector field. When you think of this a little bit, it turns out to be Maxwell equation. Actually, Maxwell equation is the simplest equation to control this divergence vector field. So therefore, we really answered the Maxwell's question 150 years ago. The ether, which produces an electromagnetic wave and produces a Maxwell equation, is a string liquid. It's a quantum string liquid. So actually, after realizing this, I just kind of surprised and puzzled why it takes so long. We should know this a long time ago. String liquid is not a very hard imagination from particle liquid. It's quite a natural generalization. Okay, and but in addition to the light, we know the elementary particle also have gluons. The gluon produce this produces a weak and strong interaction. So this gluon satisfies this Yang-Mills equation, a different wave equation. Then we ask, can the qubits liquid, the qubits ocean, produce this wave satisfy Yang-Mills equation? The answer actually is yes. Again, we are using this string idea. But now the string may have different type, like we have this blue, green, and red string. And those strings can join in a particular way. There's a certain rule for the string to join. Actually, there's a string type and how they join give us a sense of gauge group, actually determine the gauge group. And then this kind of stringlet wave would give us a Yang-Mills equation described by the gauge theory of that gauge group. So that's how Yang-Mills equation, how gauge theory, how gauge group appears. They're coming from the string type, which are representation of a gauge group, and how this string can join that tell us the fusion rule of representation. So this is so from this, actually, we get a very sophisticated long-range entanglement, which actually produce a Yang-Mills equation. Okay, so the stringlet density wave give us gluon and weak interaction. But how about electron? In the standard model, in our universe, not only have a boson, which is a gauge boson, like a photon and the gluons, we also have an electron, a quark, and a lepton. And those are fermion. They are even more strange. They are fermion. They carry fractional angular momentum. So can we produce a fermion from these very simple qubits, which actually is bosonic? It turns out that we can, because to produce this photon, we have a closed loop. The string are closed loop, but the string have an end. When string have an end, it's like a topological defect. It's a defect of a string liquid. The string end is a defect in string liquid, and this defect actually the source of string density, actually source of an electric field. So that's kind of like a charge. And also because this defect has a string attached. You may say that the end of a string is not a point particle, it's some extended object. But however, in the background of a string liquid, we can only see end of string because the middle of a string is merged with a background of closed loops. They don't cause any energy, so we don't see they are there. We only, in the background of a loop liquid, string liquid, we only see the end of string as a point like a object. But however, even though from energy point of view, we only have a point like energy, but we do have a string attached. This point particle with a string attached can change statistics. We can get the Fermi statistics, and even non-abelian statistics from this point of view. Okay, so therefore, this string liquid and the long-range entanglement not only give us a Maxwell equation and a Yang-Mills equation, it can even give us the Fermi statistics and the fractional angular momentum. Okay, so this is this really the magic of this long-range entanglement. So therefore, this string liquid provide us a unification of a gauge interaction and the Fermi statistics. So remember that the grand unified theory unified the electromagnetic interaction, weak interaction, and strong interaction, putting this all interaction in the unified framework. But however, this qubits ocean or this string net liquid can unify gauge interaction and also Fermi statistics together in one same framework, and they're all coming from the highly entangled qubits. So this is an idea. Okay, so looking back, actually, it's kind of amazing. That is, we discovered light first, and we formulated macro equation long times ago. Okay, but however, after that, we start to understand the symmetry breaking and the symmetry breaking order parameters, spin wave, and all that. And then we understand those. But however, those wave equation, this spin wave, ordinary spin wave equation coming from a weakly entangled state. But the Maxwell equation at the very beginning tell us a highly entangled state. It's really coming from a highly entangled state. But we don't know that. And only after we understand the weakly entangled state going all the way back, after we understand the highly entanglement, we start to appreciate that actually our vacuum itself is a highly entangled state. That's why we get a Maxwell equation. That's why you get a Yang-Mills equation. That's why we get the Fermi statistics. Really, because our vacuum is a very special material. It's a highly entangled material. And that gave us a so rich world. And then in condensed matter, we start to simulate a simple material first, like ferromagnets, antiferromagnets. Then after quantum Hall states, then we want to do a spin liquid. That's a time in condensed matter we try to simulate our vacuum, the material which actually we encounter first before every other material. Yeah, this is kind of amazing cycle. So under this framework, so what we have is that this long-range entanglement really gave us this unified theory of both matter and interaction. So I try to call this a second quantum revolution, because the first quantum revolution already gave us a very rich world. But actually, if we really push even further, we find that the matter and the information are really unified. And so actually, the identical particle, this Maxwell equation, Yang-Mills equation, Fermi statistics, the spin 1/2, and actually the chiral fermion can also be obtained this way, and the Lorentz symmetry is also can be included. But still, at the moment, we don't have a gravity. We don't have a graviton. So we do not have we don't know how to have some kind of organization whose wave is satisfy Einstein equation. So this is still open question. So how to get the Einstein equation is still open question. And so it's really current. We try to push very hard to see whether you can add Einstein equation. Then that's if you do that, that means we will have a theory of quantum gravity. Okay, so really to summarize that, under this quantum revolution, second quantum revolution, the new world view actually is a space actually is the ocean of qubits, and these qubits may form a string net liquid, and this fluctuation string net give us a photon and a gluon, and the end of the string give us electron and a quark. And this new actor in this new world is a many-body entanglement. And what is new mathematics? Okay. Because in this new world, we have new phenomenon for many-body entanglement. So we need a mathematics to describe all this many-body entanglement. So actually, we are facing a difficulty we are facing is similar to what Newton is facing. Before Newton, we have a simple algebra. But using this simple algebra, we cannot describe a curved motion. And so therefore, we have to invent new mathematics to describe a curved motion. Really, because the curved motion can be viewed as a new phenomenon. And then that requires calculus to describe this new phenomena. And right now, we are facing a new phenomenon. It's called many-body entanglement, or long-range entanglement. And what kind of mathematical formulation, what kind of mathematical theory allow us to describe this long-range entanglement? And this is a new challenge. And right now, we start to see this new mathematics. And this new mathematics actually have a scary name called the tensor category theory, a higher tensor category theory. It's called the fusion higher category, yeah, or Brady fusion higher category. So all this category theory in mathematics. So this category theory is a very abstract theory, but somehow it seems it's the right mathematics for entanglement. So there's another analog. Group theory is invented in mathematics, and they are invented as a tool to solve this algebraic equation, like a fourth order equation or fifth order equation, things like that. And that is group theory is invented to understand this algebraic equation. But however, then in physics, we find actually group theory is better to be a theory describing symmetry. So that's why, because physical theory have a lot of symmetry. That's why physics need a group theory to describe this symmetry. And we are facing very similar thing. The topological order coming from many-body entanglement. And this phenomenon, many entanglement, require a new theory, which is category theory. So therefore, this new mathematics actually may enter into physics, tensor category theory. And that's a sign that this second quantum evolution is very deep, because even new mathematics is required. Okay. So that's basically a summarize what I'm going to talk about. Is that from this elementary particle point of view, the matter and the space and the interaction, they all coming from these qubits. Okay, this gauge interaction, Fermi statistics, and the sense of space really coming from the long-range quantum entanglement. So therefore, this quantum information and long-range entanglement give us a kind of understanding of a lot of mystery of universe. However, in condensed matter point of view, this long-range entanglement tell us we may have a new kind of material, new kind of phase matter, and that may give us a new material property, and we can make new applications. So it's a very exciting time in both high-energy physics and also in condensed matter physics, because this long-range entanglement gave us a really new world. And then also there's interaction to the mathematical physics and the quantum information, because we really need new mathematics, new understanding quantum information to really understand all these phenomena. Yeah, thank you very much.
Thank you, Xiaogang, for a very stimulating talk. So we're open to questions. Please feel free. Let's start off with questions from students and postdocs. We have a question from Qiang Miao, Duke University. Can you please post your question? Please remember to unmute your microphone. Oh, okay. Well, maybe I can just read his question. Can tensor network states, e.g. multi-scale entanglement renormalization ansatz, encode the long-range entanglement? And how long can be called as long range?
Yeah, that's a very, very good question. Yeah. And the first let me answer the second question. What do you mean by long-range entanglement? How long is the long? Remember we're using the string liquid to describe the long-range entanglement. We say this a string liquid have a long entanglement. So how long is long can be think of how long is a string. So basically, I would say the string is very long. And the string is not 1 meter or not 1 kilometer. Actually, a string can wrap around the universe several times. So therefore, that is a, so basically when you have in condensed matter, we have a sample, we have a string liquid, which describing this new state of matter with the Maxwell equation. The string actually can be as long as large of a sample. So that really means long range. It means the size of the universe of size of your sample. Okay. And then this then also we mentioned this tensor network. That's I already say that's this tensor category theory is a very important mathematical theory to describe these highly entangled states. Now I want to say that this tensor network method actually is a very, very important method to describe, to have numerically handle these highly entangled states. Because this highly entangled states is very hard to deal with. Because our previous method, like quantization, creation annihilation operator, energy band, they are not those methods do not work well for highly entangled states. So we really have to invent a new method, new tool to do that. And I feel that tensor network is one such tool. So using tensor network, we can really, it's a way, it's a quantitative way to describe a different entanglement, a different pattern entanglement. Actually, from tensor network, you can get the state with all this stringlet condensation and get the Maxwell equation and the fermion. You're supposed to get all from that. And then there's another issue of tensor network is that there's a kind of what is this multi-scale mirror, the multi-scale entanglement tensor network. And this tensor network is a more special kind of tensor network. It's supposed to be a tensor network to describe so-called gapless states or quantum critical point. And this is the more specialized. And actually, this highly entangled states also give us a very good hint on how to handle this quantum critical point. And this is long challenging, very long-standing theoretical physics, in theoretic physics, how to have a systematic theory for quantum entanglement. This multi-scale entangled network can be used as a way to handle that. Yeah, that's a very good question.
Okay, next question comes from Nai Ziyue, Hong Kong, UST. Do you want to post the question directly? Okay, I'll just read his question. Do the string liquid model have anything the string theory?
Yeah, this is I don't know. Maybe the answer is yes and no. In the early version of string theory, the picture is quite different, and that is we view elementary particle not as a particle but as a small piece of string, like a small loop of string may give us a graviton, and the small piece of open string may give us the photon, and the string have a fermion on that, and this superstring gave us a fermion. So there, related to the first question, the string in string theory can be very short. At least that's an earlier version of string theory. It's a short string gave us these elementary particles. And this part is very different from this stringlet picture. There, the string coming from is as large as universe. It is a fluctuation of string density gave us a photon, and at one end of string gave us a fermion. And that's one difference. Another difference that in the stringlet picture, there's no fermion. We only have qubits. Everything starts with the qubits. So no fermion, no supersymmetry. But however, the string theory also undergoes several revolutions within string theory. There's a deep brain, and there's a many other things. And I think nowadays the modern and also this holographic principle understanding. So the more modern string theory, the string no longer play such a central role, although still called string theory. And so for this revolutionized string theory, it's pretty close, I would say. Yeah. So it seems getting closer, even closer for this more modern version for string theory. So actually, a lot of development in string theory now probably have a direct application for this highly entangled many-body states. So basically, what I'm saying is that there's a lot of theory developed in string theory may apply to quantum material. So that's also very exciting. Yeah.
Okay, thank you. The next question comes from Liu Kefei. Kefei, do you want to pose your question directly?
Yes. Yeah, thank you for excellent talk. I just wonder, how does the non-abelian gauge theory emerge from this picture? How does it know it's a non-abelian structure?
Okay, yeah. So let's do this a closed loop. Actually, when I say using closed loop to study U1 gauge theory, I cheat a little bit. So sometimes the two string can merge into one string. So string have a strength. You have a strength of one string, also strength two string, and strength three string. So string is labeled by integer. And this string can actually confuse. So two strengths of one string confuse into strength two string. So but this is like addition for integer. And this integer actually labeled the representation of U1 group. So fusion of a U1 group actually like an addition for integer. That's because different representation of a U1 group are labeled by the U1 chart. So fusion of a string coming from the fusion of this U1 representation. And from this, now we can understand we have a non-abelian group like a SU2 group. And then the string would have a labeled by the positive integer. And then when the strength of one string fuse, you may get a string 1 and a string 0. Because the spin 1 fusion can give you spin 1 and spin 0. And also spin 2. Yeah. So therefore, that describes a fusion rule of a string. So the string are labeled by representation. How string fuse depend on the fusion of representation. The tensor product of two representation gave us a third representation. And that's a fusion of two string give you a third string. So therefore, this string fusion and in the string net control the gauge group. And then the dynamics of this kind of string net liquid would give rise to the gauge theory. So in some sense, this kind of some version of gauge theory. Gauge theory can be formulated in this way. So therefore, this allows us to using this using the qubits, because the string coming from qubits. So that's allowed to using qubits to simulate the dynamical gauge theory. So actually, this is a very active development in condensed matter to see whether there's some quantum magnets. The low energy effect theory actually is a U1 gauge theory, or even better, some non-abelian gauge theory. Yeah. So there are theory of that, but we still don't have a material. But maybe you already have a material. Actually, I should include that slide. You know, the Lu Li from Minnesota, they just posted paper a few days ago, and they may have a spin liquid, which have a direct fermion and also have some kind of U1 gauge theory. Yeah. So this field is very active, and the people are really looking for this quantum material, which actually looks like our universe.
Good, thank you.
Okay, next question is Koshari. Would you like to pose your question directly? Okay, I'll just read. You can also integrate symmetry breaking.
Yeah, symmetry breaking is included here. Yeah, I did not emphasize that. Symmetry breaking can be understood without the long-range entanglement, and so it's here in the formalism. But I just want to say that the new feature is coming from a long-range entanglement, and so in some sense, symmetry breaking gave us a scalar theory, gave us a scalar boson. And but the long-range entanglement gave us the gauge theory and gave us a fermion theory. And so if you only have a symmetry breaking, and you usually just have some kind of a scalar boson from other parameter. And but now we know that from long-range entanglement we can get a gauge theory and a fermion. So that's a new feature.
Okay, Dingguo, do you want to? That's the question I have also. Could you please ask your question?
Hi, Xiaogang.
Hi.
Wonderful talk. Wonderful. I'm amazed you can get so much out of the string liquid. Wow. I just a very short question is that it seems like you may have derived the Maxwell equation and the Young-Mills from this string liquid, but if the dimensionality of the string liquid where it change, how this equation become, or what is the space dimensionality this your theory would reside?
Okay, certainly. When I try to apply this string liquid to particle physics, we assume the space-time is a three-dimensional space, one-dimensional time. Okay. And so it works. What I really try to say is following. In two-dimensional space, and there is a way to produce a fermion. We just bound the charge with a flux, then we get a statistical change, we get a fermion. But however, in three-dimensional space, how to get a fermion out of a boson, out of the qubits? It's quite tricky, and it's hard to get that. And then this using end of string is one way to get the fermion in 3 dimensions out of a boson. This is maybe it's a new result. And so therefore, but certainly this kind of theory, the highly entangled theory, applied to all the dimensions. In 2 dimensions, we have a lot of highly entangled state. In 3 dimensions as well, if someone can make a 4-dimensional space, certainly it's there. And but there's another dimension we should talk about. Here we think about the string. String is a 1-dimensional object, and they can form a liquid. Why don't you think about the membrane? You may think a membrane liquid. And maybe membrane liquid gave us a gravity. Actually, we tried. We said, okay, string liquid gave us a Maxwell equation. Maybe membrane liquid gave us an Einstein equation. But we failed because the membrane liquid gave us some field, a tensor field, but gave us anti-symmetric tensor field. The Einstein gravity is a symmetric tensor field. So actually, it doesn't work. And so it's a great regret. It doesn't work this way. And so we still scratch our head to see whether we can generalize a string, or maybe some dimension or some more weird membrane or something, which gave us an Einstein equation. So this dimensionality of a string and its object may give us some hint how to get Einstein equation.
So let's see. More questions? So how does your spin liquid depend on the size of the spin? Spin 1/2 versus spin 1, or?
Okay, there are 2 questions. There are 2 aspects of this question. You can see when you have a spin 1/2, then you'll say spin up is a background, spin down is your string. You don't have one type of string. Okay. When you have a spin 1, you may have a more type of string, like a spin up is a background. Then spin 0 is one type. Spin down is a second type of string. And so therefore, using this spin, different higher spin, you can get more type of string. And then you may get a string net and make a non-abelian gauge theory. So that is one aspect. And another aspect that in the material, when you have a high spin and a low spin, which material is more likely to get a highly entangled quantum states. And in that sense, a spin 1/2 is better. Because usually for spin 1/2 material, you have a stronger quantum fluctuation. It's easier to get a spin liquid using spin 1/2 spin. A higher spin is more classical. So it's harder to get a spin liquid. So actually, usually even spin 1/2 is not enough. We need a so-called frustrated lattice. Like a square lattice is unfrustrated, we get a firm magnetic state on the square lattice. So actually, in the Luli's results, they have a spin 1/2 in the cogman lattice, I think. Yeah, and then the cogman lattice in 2 dimensions is one of a very highly frustrated lattice. And the spin 1/2 in cogman lattice is likely to form a spin liquid. And that spin liquid is highly entangled. And because high entanglement, we may have emergent fermion and emergent gauge field. So that spin 1/2 favorable from material point of view to get a spin liquid.
What about anisotropy?
Anisotropy, I mean, you mean anisotropy in spin direction?
Right.
Yeah, that I don't know. Yeah, that depends, it's I won't say it's a favorable unfavorable. Certainly, if you only have Ising type interaction, that's probably not so good. But like some kind of spin orbital coupling. This this DM term, that may help. I don't know. Yeah, this is whatever increase the frustration would help. Those questions are really, really important. What I described here is just some idea that the long-range entangled state is very interesting. But what is lacking nowadays is a practical mechanism. So what kind of interaction can causing this long-range entanglement? It's like in a superconductor, we know the attractive interaction between electrons may causing superconducting states. And we like to have something more concrete. So what kind of interaction, what kind of condition favor spin liquid? Yeah, this is a pretty open, and there's a lot of research in this direction. And we are really hoping to making progress. So to make some guidance, so what kind of material is best suited to discover this kind of new phase of matter? Yeah.
More questions from the audience. What about Lorentz invariance for different dimensions?
Yeah, this is the weak point of the theory I presented. In condensed matter system, we don't have Lorentz symmetry, but we may have an emergence of Lorentz symmetry. That's like a linear dispersion relation. Actually, like in solid, the phonon have a linear dispersion relation. But we can say there's an emergence of Lorentz symmetry. But however, also in condensed matter, the emergence of Lorentz symmetry is not very natural in the sense that when you have multiple phonons, they have a different sound velocity, like a different speed of light. So there's no principle to say all the modes should have same velocity. Certainly, you can fine tune to make those modes have same velocity to have an exact Lorentz symmetry, but not natural. So therefore, from this using condensed matter to simulate a standard model, we cannot produce the Lorentz symmetry naturally. We have to do that through fine tuning. So it's very unnatural. But it's there. It can be included, but not naturally. So then that's really back for a big question. Whether Lorentz symmetry emerge as a principle, or maybe there's some symmetry or some principle which give us a Lorentz symmetry. Certainly the typical condensed matter system don't have that principle. So that's why we only have a linear dispersion relation, but we don't usually have a Lorentz symmetry. But this is again, it's a very deep question. I don't know where Lorentz symmetry comes from. Whether there's some principle, something deep, give us that. I don't know. Yeah, that's open question.
Thank you so much.
Yeah.
Any more questions from the audience?
I didn't quite get it, Xiaogang. The three kinds of strings you have, is that necessary? Three to explain the flavor of elementary particle, your three kinds of so. What is this assumption?
The string liquid is just let me put it this way. How many string we need? It's almost dynamic question. For example, to get SU2 gauge theory, you need a string labeled by this spin, like a spin 1/2, spin 1, spin 2, and etc. You have those strings, but you do not need all the repetition. When you have first a few repetition, you're probably already able to produce SU2 dynamics, you know, and so therefore I think just a few string is enough. But this became a dynamic question, and that needs to be answered via tensor network. Actually, the tensor network calculation can tell you what kind of a string interaction actually gave rise to SU2 gauge theory, and then the end of string would produce this SU2 gauge charge, which is coupled to SU2 gauge theory. Yeah. You don't need all the repetition of a gauge group to produce that gauge theory. Yeah.
So, any connection to quantum chromodynamics can somehow
using SU3 you can something can produce SU3. Yeah, maybe let me put it this way, and so in principle all this standard model can be produced, but I think what I try to say is that this kind of understanding have some kind of relevance to those so-called beyond standard model theory. You know, standard model is experimentally confirmed, but however, people believe standard model coming from something from even more unified theory, some other theory, which at the low energy produces standard model. So this more unified theory is called the beyond standard model. Okay, and this stringnet picture is one of this beyond standard model, and it's actually having some unique features, and then we hope this unique feature probably can be have some experimental relevance, you know. Like some strong speed problem and like a cosmic string, you know, things like that. And those feature different model have different prediction, and stringnet has its own unique prediction. And then maybe one can really make some experimental distinction there. Yeah.
So am I to understand that one can have asymptotic freedom then?
Sorry. Although the standard model phenomena can be produced because the stringnet at the low energy became just gauge theory. So therefore, the Euro gauge theory phenomena are all there. So they just produce a local gauge theory, and it's just a stringnet model. Just tell us actually we can start from qubits, from quantum magnets, and to produce a gauge theory at the low energy. So it's really answer the high energy, what at high energy those standard model may looks like. Yeah, it just looks like a qubits. Yeah.
So does this imply that if quantum computers come to play, one can start to simulate quantum dynamics?
Exactly. So quantum computer are made of qubits. And so here we're trying to say that we can use a quantum computer to simulate the standard model completely. Yeah. People may worry, qubits are bosonic thing. Spin flip are boson. And how can you get the fermion? How can you get the Dirac fermion with the Dirac equation? And the answer, yeah, you can do that. This can be achieved. So this stringnet basically is answer that question. How to use a quantum computer to simulate a fermion, to simulate a standard model, simulate the gauge interaction, and etc. Yeah. That's exactly what it is. Yeah.
It's really fascinating. More questions from the audience. Oh, okay. Ping-Han Chu, would you like to ask your question, please?
Yes. Can you hear me?
Yeah.
Okay. Yeah. I just wonder how many qubits you need. I think now quantum computing is improving, so maybe in near future we can do this kind of simulation.
Okay, yeah, this is a very good question. And I think currently people are already using quantum computer to simulate this stringnet liquid, and which can give rise to non-abelian statistics. And so this is so there's another aspect which I just touch a little bit. We say that to simulate the gauge theory, we need a representation. We need a string labeled by representation of a gauge group. And I say that you don't need the old representation. But here I want to say another thing, that if you do have an old representation of a gauge group, you actually can have an exact model producing that gauge theory as a commuting projection model. So people really using this exact model and in the quantum computer to simulate the stringnet and simulate these non-abelian statistics. And because this is exact model, the correlation length can be very small. So you can using a small system, small quantum computer to simulate the exact model and simulate this braiding and etc. I forgot the number. Let me see. I think maybe the some simulation I heard it maybe 25 qubits. So it's really so actually the current computer can already simulate that. But on the other hand, 25 qubits is not thermodynamic limit. So you don't have a topological protection. You can only through fine-tuning through irrational model, you can simulate this phenomena. But however, the one aspect of a topological order is that this kind of property do not need to fine-tune. Even when you add a perturbation to your model, you still have those Fermi statistics and the gauge theory. You still have that. But that requires a big system. Then, unfortunately, how big? I would say that's really big. So like in 2-dimensional, I'm thinking about 100 by 100 spin or qubits. So I'm talking about 10,000 qubits. The reason I'm saying that is that I have some experience. If you're using this about 20 or 30 qubits to simulate this generic system with topological order, it's barely, you don't see scaling, but barely you see ground degeneracy, but not very degenerate. I tried this. But I believe when you have 1,000 qubits, maybe 10,000 is a little bit too much, but 1,000, you should do pretty good job. You should get very good protected ground degeneracy. That's actually became protected qubits, topological qubits. So I imagine when you're able to get 1,000 qubits, you can start to probe this universality behavior. At the moment, with 25 qubits, you can simulate the exact model, but you need to fine tuning, so not universal. Maybe 1,000 qubits probably is you need that. So this is the reason why I push for tensor network, because if you do exact diagonalization using ordinary classic computer do exact diagonalization, you cannot do 1,000 qubits. You can only do maybe 30 qubits.
I thought tensor network only works well for one dimension.
Yeah, that's also a very good point. It works well in one dimension. And so therefore, people talking about the two-dimensional tensor network for tensor network for two-dimensional quantum system or three-dimensional quantum system for quite a while. And one needs some breakthrough to go to higher dimension. So the tensor network still is a very open frontier. One needs a breakthrough. And but here I think the breakthrough is technical, it's not fundamental. So there's some kind of trick we need to invent. And so therefore we can use tensor network to simulate a 2D, 3D cis-quantum system. And then we can really design material using tensor network first. We just design Hamiltonian, simulate with tensor network so that we see whether this ground state have a long-range entanglement or not. And then we can try to see whether this kind of Hamiltonian can be realized in material or not. And so Albert, you have really very good point that we have this kind of cycle in one-dimensional system. In one-dimensional quantum system, we can simulate that very reliably using tensor network. We cannot do that for two-dimensional quantum system. Yeah, we need some breakthrough there.
More questions? We would really ask Xiaogang many questions. He has been so kind to give us a real flavor of the depth these things involved. Shall we give Xiaogang a chance to rest now? And let's thank Xiaogang Gao again for a wonderful talk. And
yeah, thank you for this opportunity. I do feel this is a really exciting field. Many things are happening. So a lot of open question, open direction. Yeah, it's a pretty exciting time.
Okay, so with that, we will close. Should we allow people to just chat? Because there are a lot of old friends who have not seen each other for a while. And some may want to say hello to Xiaogang.
Yeah, I guess that's a great idea. And,
yeah,
okay.
I fully support. Maybe keep the Zoom open for everybody until.
Yeah, let's keep the Zoom open. And Xiaogang may kind of stop the sharing so we get to see the video better.
Yeah.
Let me suggest we give Xiaogang a chance to get a drink of water or something because he's.
Okay, maybe I'll get some drink of water. Yeah.